In the last class, we discussed the discovery of electron and nucleus. We saw different models of atoms. We discussed about the Dalton's atomic model. Then we discussed Thomson's plum pudding model, and we also learnt about the Rutherford's atomic model. In today's class, we will begin with by discussing what is this nucleus made up of. We will first learn about the stories of the discovery of those internal structure of the nucleus. This is what we are going to do next. That was answered by the German physicist Eugen Goldstein from his series of anode ray experiments. These experiments are very similar to the cathode ray tube experiments with two important changes. One, first of all, he took a glass tube as it was in the cathode ray tube. One important change is that it was not completely evacuated, rather a small pressure of gas was maintained in the glass tube. Okay. And then of course, these tubes have two electrodes, they were fixed with two electrodes. Let us and they were connected to the other difference that was done was, if you remember, in the cathode ray tube we had one hole in the center of the anode. Here what we do is that we create, so now the way we have applied the potential difference, the polarity, so just that this is my cathode, negatively charged electrode, this is my anode. What is done is that we have used a perforated cathode. So, there are I am drawing 3 holes here, and the anodes are this is my anode plate. All right. So, the second change is that we have used a perforated cathode, and we are applying high voltage. When we apply high voltage, we know that cathode rays will start from cathode and they will travel to anode. But when these cathode rays, which are now the series, we know that they consist of electrons, the particles electrons, when they come, they hit on these gas molecules which are present in this glass chamber. And when they hit these gas molecules, they ionize these gas molecules which are present here. By ionization, what happens is that these gas molecules, they lose some electrons, and when they lose that electron travels towards the anode, and the cations, after removal of the electron, this positively charged gas cations, they get accelerated towards the cathode plate, because they travel, since they are positively charged, they travel from anode to cathode. So, we see some rays now from anode to cathode, and these are positively charged. Since we have perforated cathode plate, so these rays, they pass through the cathode and they again can hit the screen. We can have the zinc sulphide coating here, so that we can see the bright light when the rays hit the screen. Now, again you can redo the experiment that was done by J.J. Thomson to show that here are these rays which travel in straight line from anode to cathode. They travel from anode to cathode, and we call them therefore anode rays, and you can show that they are positively charged, and they will you can also carry out several experiments and determine their E by m. What was however observed here, that this E by m, the charge to mass ratio, depends on the nature of gas. Depends on the nature of the gas. So, if you use hydrogen, you have a certain value of E by m. If you use helium, it has got certain some different values of E by m for these anode rays. So, these are called anode rays here. By doing several experiments, it turned out that the smallest positive ion was coming from hydrogen. That was the smallest, the lightest ion that had the smallest mass, that was coming from hydrogen atom. Right. And in 1919, it was shown that this hydrogen ion is called what we know as was proton. These protons, they are present in all the elements, they are the center of the positive charges, they have some the charge that was discovered for this proton was exactly the same charge that of electron, but it is now positively charged instead of electron which was negatively charged. Its mass was discovered, which was to be which was found to be about 2000 times heavier than an electron. So, from this anode ray experiments, we realized that the nucleus contains protons, which are the center of positive charge, which are also the particles that provide mass to the nucleus. But then there was another problem that we will discuss now. For example, when it was observed that hydrogen atom, let us consider hydrogen atom. So, it was seen that according to Rutherford's model, we can draw that the nucleus contains one proton, and of course, there is an electron. The electron is massless compared to the proton. So, the mass of this atom is primarily coming because of the presence of one proton. So, we have mass of hydrogen from Rutherford's model. I mean, we can get the mass from doing experiment. Then let us compare it with helium. So, helium has got 2 electrons and it has also a nucleus, and this nucleus has now got 2 protons, right. So, the number of protons in helium atom is double that of the number of protons in hydrogen atom. This would indicate that since it is only the proton which gives rise to the mass of the atom, it would suggest that the mass of helium atom must be twice the mass of hydrogen atom. However, the experiments showed that mass of helium atom is somewhere close to the close to 4 times of the mass of hydrogen atom. That was surprising. Why should that happen? How is helium getting more mass? Where from is it getting more mass? This is one question. The other question is that if you look at the nucleus, now the helium nucleus has 2 protons, they both are positively charged particles. So, why are they not repelling away from each other? So, why is helium nucleus still stable? They should simply go away from each other. This could not be explained from Rutherford's model. It was in 1932 that James Chadwick, he did a series of experiments and discovered that nucleus of course contains protons, as we have discussed earlier, which are charged particles. In addition to protons, it also contains a new set of particles, that he called as neutrons. These neutrons are chargeless, so they have 0 charge, and it was found out their mass is equivalent to mass of a proton. It was after James Chadwick's discovery of neutron, it turned out that helium atom, in addition to 2 protons, it also has 2 neutrons, and since the mass of neutron is equivalent to the mass of proton. So, therefore, in the nucleus of helium atom we have 2 protons, 2 neutrons, and in case of the hydrogen we have got only 1 proton, and this explained why mass of helium is nearly 4 times that of mass of hydrogen. So, we can summarize now the subatomic particles that we discussed. We saw electron it has a charge 1.6 into 10 to the power minus 19 coulomb, which is negatively charged. We discovered, we came across proton, which has exactly the same charge as electron, but it is now positively charged, and we have a third particle, which is neutron, which is chargeless, or it has 0 charge. In a relative charge scale, we can say that electron has -1 charge, proton has +1 charge, and neutron has no charge. When you look at the mass of these particles, we see electron has mass of 9.1 into 10 to the power minus 31 kilogram, proton has 1.6 into 10 to the power minus 27, which is nearly about 2000 times heavier. The proton is heavier than electron, and the mass of neutron is nearly equivalent to the mass of proton. In AMU scale, atomic mass unit, we can say that the proton has 1.007 AMU mass, neutron has 1.008 AMU. We can roughly say that neutron has 1 AMU mass, proton has 1 AMU mass, and electron is massless, almost nearly 0. In this way, we discussed about the discovery of electron, proton, neutron, how the nucleus is made up of, the individual charges and their mass of these fundamental particles. Let us summarize first before we start any further. We discussed about electron, I call it E minus. Then we also had proton, I call it P plus, and then we discuss about the neutron, N. These are the 3 fundamental particles that we discussed. Let us make this table. We have charge, we have mass. If you remember, electron had relative charge of -1, proton had a relative charge of +1, and neutron is a neutral particle. So, therefore, there is no charge, charge is 0. When you looked at the mass, which we knew that we got to know that proton and neutron, they have 1 AMU mass each, roughly equal. Compared to the mass of neutron and proton, the mass of electron is negligibly small. Therefore, we took it as 0. So, this is the charge and mass scenario of our subatomic particles. Using these 3 subatomic particles, we would try to identify atoms. We will now spend some time in discussing or establishing the identity of an atom. Right. Identity is a very important issue. If I want to find out about you, what would I do? I would first ask, well, I want to know this student from this school, but that is not a sufficient information to find you out, because your school will have so many students. Then I will say, okay, I need a student who is studying in this school and who is in class 11th, for example. But in your class 11th, there are so many students. So, I have to tell that, okay, I need this student who studies in this school in class 11th, and his roll number is this and this. That will be an exact identity of yours. Similarly, to identify an atom, or to establish the identity of an atom, we need some identity indices. The most important is what is called as atomic number. This is given as symbol Z. This is nothing but the number of protons in your atom, in the atom. All right. But atomic number alone is not sufficient to establish the identity of an atom. We need another quantity, and that is called as mass number. The mass number is given by the symbol capital A, which actually signifies the mass of the atom. From this table, you already know that which of the particles contribute to the mass of the atom. Certainly not electron, because electron has very little mass, is negligible. So, proton and neutron, they contribute to the mass of the atom. So, therefore, when establishing mass number, we say number of protons plus number of neutrons. But we already know the number of protons is given by Z. So, mass number is Z plus the number of neutrons. These two are very important quantities, but in addition to them we also require another quantity, and that is the charge on the atom. Let us call it by small q. How do I determine the charge? Why do I have charge in the atom? Because I have got two different charged particles, two different types of charged particles in the atom. One electron, which is negatively charged, the other is proton, which is positively charged. Neutron does not contribute anything towards charge. So, when I am trying to establish the charge of an atom, I can safely ignore the neutron. So, the charge of an atom is given as number of protons minus number of electrons. This minus is coming because electron has negative charge and proton has positive charge. So, this equation would actually fit. Let us take some examples. Let us say I have an atom which has 5 protons. So, 5 p plus, each proton has plus 1 charge. So, the protons contribute plus 5 charge, and let us say I have got 5 electrons, each electron has minus 1 charge. So, therefore, net contribution of charge from the electron side is minus 5, and when I combine them plus 5 minus 5, I got the total charge as 0. If I had 5 protons and 6 electrons, so you know that this is 5 plus and this is 6 minus, total charge is minus 1. Similarly, if I had 5 protons and only 4 electrons, so plus 5 minus 4, that gives me plus 1. So, this way I can obtain atomic number, mass number and charge. These three quantities are sufficient to describe the identity of an atom. We will use these concepts and take some examples to clarify our knowledge further. All right. Our first example, let us call example 1. Let us say I will use this hash sign for number. So, let us say I have a system where number of proton is 6, number of electrons is again 6 and number of neutrons is 6. What can we say about this atom? All right. We know that the atomic number of this atom, that is Z, is given as 6. The mass number of this atom A, which is number of proton plus number of neutrons. So, 6 number of proton plus 6 number of neutrons, that is 12. The charge of the atom, which is obtained by number of proton minus number of electrons. So, in this case 6 minus 6 and that is 0. So, we have got an atom whose atomic number is 6, mass number is 12 and charge is 0. That is a shorthand notation way of writing all this information. The shorthand notation is given in this way. It is written as Z A x. So, Z is the subscript of x, A is written at the superscript of x, both Z and A are written at the left of x, and on the right hand side, right hand superscript of x, you write the charge. This is a shorthand notation of an atom. Let us see, we know Z, we know A, we know Q, but what we do not know is this x. This x is nothing but the chemical symbol corresponding to the value of Z. For example, let us take this example. Here Z is 6, so I can write 6, A is 12, I can write 12 in the place of A, and then charge is 0, but what should I write in the place of x? This chemical symbol corresponding to Z value of 6, if you check periodic table, I hope you know it by heart, it comes out to be carbon. So, we call this element as carbon, whose atomic number is 6, whose mass number is 12 and which has no charge. This is also equivalently written when the charge is 0, one does not need to specify the charge. So, therefore, you can equivalently write C 6 12 in this way by ignoring the charge, and this is done when Q is 0. you can see that this 6 corresponds to carbon, or carbon corresponds to the value of Z as 6. So, therefore, these two are writing both these information is perhaps unnecessary. So, again equivalently you can write C 12 just like this, because by writing C you already signify that Z or the atomic number is 6. So, you do not need to write. So, these three equivalent way of writing is normally done. Let us look at another example. In this case I have number of protons is 16, number of electrons is 15, number of neutrons let us say it is 18. So, what is my Z? Z is number of proton, that is 16, that is very good. What is my mass number? That is A, which is number of protons plus number of neutrons. So, 16 plus 18 which is 34. What is the charge? I see here 16 positive protons, 15 electrons. So, 16 positive charges, 15 negative charges, that gives me 16 minus 15 which is plus 1. How would I write down in the shorthand notation? Of course, so Z is 16, A is 34. If Z then it Z is 16, then the symbol is sulfur and the charge is 1. So, this is the atom that I found out. We will take 2 more examples and try to understand what more information can we get. Let us take another example. Let us say we have this information Cu 2963. So, this is copper atom whose atomic number is 29, whose mass number is 63, and we have to find out the number of electrons, protons, neutrons, the charges on this. So, of course, the charge is given as 0. So, what I know? I know Z is 29, A is 63, Q is 0. So, number of electrons I can let us find out number of protons first. Number of protons is atomic number. So, this is 29. Since the charge is 0, so number of electrons must be equivalent to number of protons, and number of neutrons is A minus Z, which is 63 minus 29, and that is 34. We got that. Let us look at another example. This time it is calcium 2 plus, mass number is 40, atomic number is 20. This 2 plus or 1 plus or 2 minus, this represents this atom is actually in an ionic state. So, this is a cation. In this case, of course, Z is 20, which is the atomic number, mass number is 40 and charge is plus 2 or 2 plus, I do not. Alright, so let us find out how many protons are there. It is easy because Z represents the number of protons. So, number of protons are 20. How many neutrons? Since mass number is 40, so 40 minus 20 is 20, there are 20 neutrons. How many electrons? You see, the atom has plus 2 charges and plus charges are coming because of proton. So, I have got 20 protons and the atom has got 2 positive charges. That means, number of electrons present in this atom must be 2 less than the number of protons. So, if number of protons is 20, so number of electrons are 20 minus 2, which is 18. All right. We will take a few more examples because this is very important concept. Let us now take 3 different atoms, C612, C613, C614. So, you see there are 3 different carbon atoms. In each of them, the Z, the atomic number is 6, the mass number varies from 12 to 13 plus 14. All right. Let us establish number of protons. Of course, 6, 6, 6 because this is Z value, number of electrons. All 3 species are neutral. So, number of proton is equivalent to number of electrons. So, that is easy. Let us find out number of neutrons. The mass number in this C612 is 12. That means, there are 6 protons plus 6 neutrons. In this case, the mass number is 13, the atomic number is 6. So, number of neutrons is 13 minus 6 is 7. In this case, mass number is 14, atomic number is 6. So, number of neutrons are 14 minus 6, which is equivalent to 8. Now, what we see here is that there are 3 different elements. They have same value of Z, they have different values of A, and that is happening because they have different values of neutrons. When 2 or more elements have same Z and different A, that means same atomic number, different mass number, we call them isotopes. So, carbon 12, carbon 13, carbon 14, they are 3 different isotopes of carbon. In nature, sometimes you would see carbon 12, sometimes you would see carbon 13, sometimes you would see carbon 14. So, whenever we talk about isotopes, they also come with their natural abundance. For example, C12 is the most abundant carbon form, which comes about to be almost 99%. C13, carbon 13 is roughly 1%, and carbon 14 is seen in the nature, but it exists what we call as in trace quantities. It is very tiny amount and almost negligible, but it does exist and it has very important properties. So, we saw when 2 or more atoms have same atomic number, but different mass numbers, we call them isotopes. We will take one more example of isotope, and that is our example number 6. These are now the isotopes of hydrogen. So, we have 3 different forms of hydrogens. In each case, Z is atomic number is same, that is 1, and the mass number changes from 1, 2 to 3. So, of course, it is very easy. Number of protons is all 1, number of electrons, since they are neutral, so all 1, number of neutrons are, in this case, the mass number is 1, atomic number is 1. So, number of neutrons are 0, there is no neutron. In this case, mass number is 2, atomic number is 1. So, number of neutrons is 2 minus 1, 1, and in this case number of neutrons are 3 minus 1, which is 2. So, we see that these 3 species, they have different number of neutrons. This hydrogen 1 is called as protium, hydrogen 2 is called deuterium, and hydrogen 3 is called tritium. Their natural abundance, protium is 99.985%, deuterium is present in very small quantities 0.015%, and you can see tritium is present in trace amount. Right. So, these 3 are again isotopes. These are the isotopes of hydrogen. Let us take one more example. In this time, this example, this is hydrogen 3, and I am going to compare it with helium 3, but helium's atomic number is 2. Again, let us write down number of protons. So, number of protons in this case is 1, number of protons in this case is 2, because this is helium. Number of electrons, both are neutral. So, therefore, number of electrons must be equal to number of protons in each case, and number of neutrons. In this case, you would see how many neutrons are there. Mass number is 3. So, 3 minus 1 is 2. In this case, number of neutrons are 3 minus 2 is 1. So, number of neutrons are 2 or 1. In this case, if you see, these 2 species have same mass number, same value of A, but different Z. Same mass number, different atomic number, same mass number, different atomic numbers. When you have such a case, we call these two species as isobars. So, hydrogen 3 and helium 3, they both have same mass number, but they have different atomic number. So, therefore, they are called isobars. We will take one more example, and that will be our last example. Let us consider these three species: sulfur 36, chlorine 37, calcium 40. Let us find out number of protons. In this case, it is sulfur, number of protons are 16, chlorine, number of protons are 17, calcium, number of protons are 20. I know this from periodic table. Number of electrons, since all three species are neutral, so number of electrons are equivalent to the number of protons, otherwise they will be charged. Number of neutrons, number of neutrons, in this case there are 16 proton, 36 mass number. So, number of neutrons is 36 minus 16, which is 20. In this case, number of protons are 17, mass number is 37. So, number of neutrons is 37 minus 17, 20. In this case also, number of neutrons is 40 minus number of proton is 20. So, therefore, 40 minus 20 is 20. We see these are three different species. One is sulfur, another is chlorine, another is the third one is calcium. But what we see is that they are related to each other in terms of number of neutrons. So, they have same number of neutrons. When we have such a situation, we call them isotones, when the number of neutrons are equivalent in two or more number of species. So, in this way we learned about how to use the number of electron, number of protons, number of neutron information to define an atom, how we can discuss about isotopes, isobars and isotones. So far we have seen the subatomic particles in an atom and how we can use this information to define or to identify an atom. Now, we will learn about something else which is very important in atomic structure, in the understanding of atomic structure, and that is light, or we also call it radiation. We will use both the terms interchangeably. All right. You might wonder that we are supposed to learn about atomic structure. Why were we talking about light? Light plays a very important role in determining the structure of atoms and molecules. The branch of science that we call spectroscopy has given us a huge amount of information about the structure and properties of atom simply by interacting light or radiation with matter. So, we need to understand the properties of light, the nature of interaction between light and matter to be able to understand the structure of matter, the structure of atoms, structure of molecules properly. So, we will spend some time in discussing about light. Light, although we use it all the time, but the nature of light has kept scientists busy for long period of time. During Newton's time, light was believed to be like particles, the famous Newton's corpuscular theory. But afterwards, so for some time light was believed to be a particle. Then afterwards, several experiments showed that light has wave-like properties, because light showed diffraction, light showed interference, which are typical wave properties. So, since light showed this diffraction and interference, it was believed that light behaves like a wave, light is a wave. Afterwards, we would discuss during this course of our discussion, afterwards there were so many experiments which were coming out, which could not be explained if we invoke the idea that light is a wave. So, on the other hand, when used light as a particle, we could again explain all those experiments, all the observations that we experiments were showing us, we could explain them. So, now light is a particle, sometimes light is a wave. At the end of our discussion, we will come out with this, that light is both wave and a particle. So, this is called duality of light. So, light can be a wave, light can be a particle, depending on the experiment that we are trying to explain, depending on the action that light is carrying out, light adopts a particular form. It is either wave or particle, but it is always both wave and particle, and it can choose whichever face of itself to show that it wants. All right. We will first spend some time in discussing about the wave nature of light. As I said, light was believed to be wave because it showed diffraction and interference, and these properties are, these features are typically seen in the wave. So, therefore, light was believed to be wave. In fact, for some time light was believed to be a transverse wave because its property matched with many other transverse waves. But afterwards, after some time, James Maxwell suggested that, well, light is a wave, but it is a special kind of wave. It is not an ordinary transverse wave. What he called is that light is an electromagnetic wave. This is a special kind of wave, as the name suggests, that it has got an electric component in it, it has got a magnetic component in it, and it is a wave. So, it is a special kind of wave that James Maxwell proposed. So, as the name suggests, that this electromagnetic wave or electromagnetic radiation has got an electrical component, electrical field and magnetic field. So, this wave, when it propagates, it produces an electric field, it produces a magnetic field. There is some interesting aspect about this electric field and magnetic field that it produces. So, this is, in this picture you see that the light is being propagated along this direction. When the light is propagated, it produces an electric field, which is given by this red line. Let us call this as electric field component. And it also has got a magnetic field component, which is given as in the blue line. So, when light is propagated, it produces an electric field and a magnetic field, but what is interesting is that the electric field and the magnetic field that it produces, they are orthogonal to each other. So, you can see in this picture, you can see the three Cartesian axes here. So, call this as origin. So, this is one direction, call this as z, call this axis as x, call this axis as y. So, in this diagram I am showing that electric field is appearing along x axis. So, you can see the propagation of electric field is along x. The magnetic field appears along y axis in this plane, and the propagation, the wave, which has now electric component and magnetic component, the wave when it is propagated, the direction of the propagation of this wave is perpendicular to both electric field component and magnetic field component. So, the wave is actually getting propagated along this direction called z direction. If the light wave is getting propagated along one direction, it produces an electric field which is perpendicular to the direction of propagation, and it produces a magnetic field which is perpendicular to both its direction of propagation as well as the electric field component. So, this is a special nature of this electromagnetic wave or electromagnetic radiation. All electromagnetic radiation show this kind of behavior. All right. So, this is one important property of electromagnetic radiation. The other electromagnetic property that we would study is that we would appreciate is that electromagnetic radiation or electromagnetic wave to be propagated, it does not require a medium. What does that mean? It does not require a medium. That means it can be propagated, it can move in vacuum. This is unlike any other wave. Other waves require a medium to be propagated, to move, but electromagnetic radiation, they do not require any medium to move. So, therefore, it can move in vacuum, This is a very important property. A third property is that all electromagnetic radiations, all electromagnetic waves have same speed in vacuum, and this speed is actually a constant, and this constant you would know as speed of light, which is given by this constant is given as 3 into 10 to the power 8 meter per second. This is the speed of light that you would know. So, the electromagnetic radiation, which is light is an example of that. This electromagnetic radiation has electric field component, magnetic field component, they are perpendicular to each other. To move, it does not require a medium, and all electromagnetic waves travel at the same speed, that is in vacuum they travel at the same speed, and the speed is 3 into 10 to the power 8 meter per second, which you know as the speed of light. Next, we will discuss about some properties or some characteristic of a wave, because we are discussing light as a wave. So, we will spend some time characteristics of a wave. When you see wave, I will show you one example of a wave. Here you see it's a wave where you see this is the normal position. So, you have created some disturbance, that is why the system is now getting displaced. So, whenever it is going away from this normal position, which is this horizontal line, that is called a displacement. We require some characteristic property to define a wave. The first thing that we need is what is called an amplitude. See, if in this wave, at every point you see some displacement. At this point you see a displacement like this, at this point you see another displacement, another value of displacement like this, and then in this direction the displacement is along other direction. At one point of time you would see that the displacement is maximum, and this value is called, the distance between this from the normal position is called amplitude. This distance is called amplitude. If you compare two the place where maximum the amplitude is seen or maximum displacement is seen, we call them crest. If you look at two consecutive crests, the distance between them is called wavelength. The other property that we need to understand is wavelength. As the name suggests, it is a form of length. We call that, we signify that as lambda. The unit that we use, it can be any length unit, but in our discussion we will use the unit of nanometer or angstrom. All right. So, this is another property, the characteristic property of a wavelength that we need to know to define a wave. While if we know wavelength, we have already a lot of information about the thing, but then we will come across another term often, and that is called a frequency. What is a frequency? You see that the wave is actually propagating. So, the wave will move. The frequency is that if you sit at any point here, let us say I am sitting here and the wave is getting propagated at a particular speed. Since it is I am discussing about an electromagnetic wave, its speed is 3 into 10 to the power 8 meter per second. So, it has a fixed speed that it is getting propagated through in vacuum. Alright, so I am sitting here and the wave is getting propagated. I will count in 1 second how many wavelengths are passing by. So, I will just move this wave here. So, I am sitting here, my pen will stay here and I will move it. So, I assume that I am moving it at the speed of light. Of course, I cannot do that. So, when I will do it again, I am here and I am moving the wave and then I see. So, I would keep on, my pen is static and the wave is moving, right. I will say that in 1 second how many wavelengths I am encountering. So, you will see that number of wavelengths that I see at one position in 1 second is called frequency. So, it is a certain number of wavelengths per second. So, that is known as frequency, and since it is given as the symbol nu, and the unit will be, since it is a number per second. So, it is second inverse, or it is also called as hertz after the scientist Heinrich Hertz. All right. Okay. I see that this is my wave. I will show you another wave. Look here. What is the difference that you see? This wave has this wavelength and this wave has got another wavelength. If you compare, obviously this wavelength is greater than this wavelength. I have tried to keep the amplitude of the two waves same, only I am changing the wavelength. Here lambda is less. Now, what will happen to the frequency? You see, frequency, to get the frequency I have to sit at one point, wherever I can choose any point, I am choosing here, and I have to again move this wave, get propagate, and I see in 1 second how many wavelengths am I crossing. So, since the lambda is small here, the wavelength is small. So, you can imagine that in 1 second in a given time, I will cross more number of waves for this wave than this wave with larger wavelength, right. So, that means, so when my wavelength is small, I would see more and more number of waves passing by in 1 second. So, when my wavelength is small, frequency is large. When my wavelength is large, the frequency is small. So, there is an inverse relation between wavelength and frequency, and this proportionality constant between this wavelength and frequency is actually given by the speed of light, because both the waves are actually, since they are electromagnetic waves, both the waves are actually going at the speed of light. So, we have this relation which is lambda into nu is given by c, which is the speed of light, which is a constant. This is very important relation. We sometimes come across another terminology, and that we call as wave number. It is nothing but we signify as nu bar. This is nothing but reciprocal of lambda, 1 over lambda. The unit that we use to define it is nanometer inverse or angstrom inverse, essentially any length inverse unit, but we will use nanometer or angstrom. Wave number is essentially the number of wavelengths that you can fit in per unit length. This is essentially the reciprocal of wavelength. We will take one small example. Let us say we have a wave whose wavelength is 5000 angstrom. Find out what is the value of frequency, find out the value of the wave number. Okay. This is so right. Let us solve it. Lambda is 5000 angstrom. You know, 1 angstrom is 10 to the power minus 10 meter. So, I have 5 into 10 to the power minus 7 meter. This is, I am converting the unit to SI. So, lambda is now 5 into 10 to the power minus 7 meter. And how do I get nu? Because I know lambda multiplied by nu, the frequency, is c. So, therefore, nu is c divided by lambda. You see, nu is inversely proportional to lambda, but the proportionality constant is the speed of light. So, speed of light I know 3 into 10 to the power 8 meter second inverse, lambda is 5 into 10 to the power minus 7 meter, which will give me 0.6 into 10 to the power 15 meter cancel out. So, second inverse, or I can write it 6 into 10 to the power 14 hertz. All right. Similarly, this is the frequency corresponding to the wavelength of 5000 angstrom. Similarly, I can also get nu bar, which is nothing, which is easy, 1 over lambda. Lambda is 5 into 10 to the power minus 7. So, therefore, this comes out to be 1 divided by 5 into 10 to the power minus 7 meter, which is nothing but 0.2 into 10 to the power 7 meter inverse. All right. So, here we learned about the characteristics of wave. As you can see, the electromagnetic radiations come at, they may come at very different values of lambda. When the lambda changes, the frequency would change, keeping the value of c constant. We will now see, we will now compare different electromagnetic radiations with different values of wavelengths frequencies. This is called electromagnetic spectrum. In this diagram, you see what is called as electromagnetic spectrum. In this axis, you see there are some numbers 10 to the power 24 to 10 to the power 12, 10 to the power 6, 10 to the power 0, which is essentially 1, and these numbers are expressed in the units of hertz, which is frequency. And in the same diagram, the lower scale shows the numbers which are expressed in as wavelength in the units of meter. It goes from 10 to the power minus 16 to 10 to the power 8. It is quite a wide range of wavelengths, quite a wide range of frequencies. Let us look at very high frequency, that means the wavelengths are extremely small, 10 to the power minus 16 meters. These energies are called gamma rays, they have extremely high energies. As you go higher and higher in wavelength and therefore lower and lower in frequency, you will come across X-rays which have 10 to the power minus 10 meter wavelengths, and these X-rays are used to ionize substances and also take X-rays of our body. In last class, we saw how X-rays were used in Millikan's oil drop experiment to ionize the gases inside. As you go higher in wavelength, you come across this ultraviolet radiation. You perhaps have heard about ultraviolet radiation, which comes from the sun. Because of the depletion in ozone layer, the UV radiation comes, and when it interacts with our skin, it can cause skin damage. After ultraviolet comes the visible. This is very important range, because this range of wavelengths is what we use to perceive things. Our eyes can perceive these colors, these 400 to 750 nanometer wavelengths. I will come back to this visible spectrum in a moment's time. Before that, let us go across. After UV, you get visible. Visible starts from violet, ends with red. Before violet, it was ultraviolet. After red, it will be infrared. There is infrared radiation. As you go further, it is microwave radiation, the radiation that you would use in the microwave oven. And further when you go, you see at larger wavelengths, these are radio waves. These are used for transmission of your radio programs, FM, AM, you must have heard. And finally, at very long wavelengths, you will see these are called long radio waves. And these their wavelengths are 10 to the power 8 meter, or the frequency is simply 1. That means what does it mean? That if I sit at one point and I will check how many waves are passing by, I would see in 1 second these waves are traveling at the speed of light, 3 into 10 to the power 8 meter per second. It is a quite high speed. Even then, I would see only one wave passing by me every second. So, that means these frequencies have extremely large wavelengths. Now, let us come back to this visible spectrum. We have of course V, violet, indigo, blue, green, yellow, orange, red. This is the visible spectrum that goes from 400 to 750 nanometer. The red light has higher wave number, the red lights have higher wavelength, and blue lights have lower wavelength, and that is why you see red light in the traffic signal, so that you can see the light from far. The blue light have low wavelength, but have high frequency, and this blue or violet light is what you see flame in the gas stoves. In this class we discussed about the wave nature of light. In next class we will discuss about the other properties of light. Thank you.